On behalf of Phoenix Integration, welcome and thank you for joining us for today's webinar presentation entitled Model-Based Systems Engineering, Requirements Development, System Design, Process Integration, and Design Optimization for Systems Engineering of Textile Machines. Today's webinar will be presented by Dr. Sven Kleiner from Engineering Methods. Dr. Sven Kleiner is responsible for the business area CAD and CAE. In addition, Sven Kleiner is Chief Operating Officer, responsible for business operations, and thus the departments of finance, personnel, as well as project management and controlling. Dr. Sven Kleiner began his career in 1995 with ABB Flexible Automation GmbH in Friedberg in customer service, and from 1999 served as a research assistant at the TU Darmstadt and the Department of Mechanical Engineering at Department of Computer Integrated Design. He received his PhD in 2003 on the topic Federative Information Model for the System Integration and the Development of Mechatronic Products. In 2009, Sven Kleiner was appointed as a lecturer for CAD at the University of Applied Science Darmstadt and offered courses at the Department of Mechanical and Plastics Engineering. Moreover, Dr. Sven Kleiner is a member of the VDI Technical Committee, Knowledge Management and Engineering, and Knowledge-Based Design. The presentation today will run approximately 45 minutes long. Following the presentation, we will open the floor to questions. To ask your question, please use the Q&A feature in your WebEx window. We recommend that you view the webinar in full screen. To do so, please click the down arrow in the lower right-hand corner of your screen, scroll to View, and select Fit to Viewer. We are also recording this presentation today, and you will be notified via email once the video is available for download from Phoenix Integration's site. And now I will turn it over to Phoenix Integration's Dr. Scott Reagan, who is facilitating today's session. Scott?
Okay, thank you, Carl. I am just going to take a few minutes to introduce Phoenix Integration for those who might not know us so well. I want to leave most of the time for Sven's presentation. I want to start here by talking about a symphony orchestra. I assume most of the people on here have been to see the symphony before. And if you're like me, you may wonder when you go why the conductor gets so much attention from the audience. Most of the applause, most of the standing ovations and such. And it's a little bit strange because the conductor obviously is not playing an instrument himself or herself. And the conductor is certainly not there to teach people how to play their instruments. Most symphony orchestras that you go to, the individuals in the orchestra have devoted their entire lives to their instrument, and they certainly don't need to be taught how to play it. But at the same time, I think we all intuitively understand why the conductor is important. The conductor is choosing the music that will be played, but more importantly, what the overall interpretation of that music will be. And then once that interpretation has been set, coordinating all these individual experts to achieve a good result, making sure everyone plays in the same tempo, making sure that the individual sections of the orchestra are balanced in the way that has been decided, making sure that the individuals and the individual groups listen closely to each other and that everyone's on the same page. And if you've been to a good concert before, you know that the end result can be much more than what you might think the sum of the parts would give you. So my question is what if you had a conductor for your engineering team or your engineering groups, someone who could coordinate, make everyone more efficient, someone who could promote collaboration and interaction among the different teams, and someone that could just get everyone working more efficiently so that better decisions could be made. And that's really the role that I see that Model Center has for an engineering group. Model Center consists of three main capabilities, the first being Model Center Integrate. Model Center Integrate is the piece of Model Center that will allow you to go and automate any of the software tools that your team might use, regardless of what computer they're on or what operating system they might be running on. And then to take those automated tools and tie them together to create automated workflows. So think of creating an automated flow chart out of your existing tools, whatever they happen to be. So that has huge efficiency gains and also helps to reduce errors. And then once those automated workflows exist, that's where Model Center Explorer comes into the picture. Model Center Explorer lets you run that workflow over and over in a way to help you gather the information you need to make better decisions. So think about things like design of experiments, like optimization, like probabilistic analysis, and also to visualize all those results so that you can understand trends and make better decisions given the information that you're able to create. And then finally, Model Center Organize is the piece that helps to capture all of this data that you're generating, share that across your engineering teams, across the individual engineers, promote collaboration, and also just manage that data so that you can reuse data where it makes sense to do so, avoid rework, those kinds of things. So those are the main capabilities of Model Center. And Model Center can be deployed either on the desktop or it can be deployed on a server in your organization to give a lot more people access to those capabilities. And we refer to that server deployment as cloud deployment. So I want to go now and introduce Dr. Sven Kleiner, who is going to talk about how he has used Model Center with some of his customers in Germany, and specifically talk about his use of one of our modules called MBSE Pack. So MBSE Pack helps engineers to, once they've integrated all their software tools, to connect those to a system architecture model, and helps to improve the efficiency of a complex system design by linking engineering tools to system architecture models. In Sven's particular case, involves some work that they've done with Meyer in Germany. So I want to go ahead and turn things over to Sven. Sven is as Carl said, the COO for Engineering Methods in Germany, and Engineering Methods is our partner in the German market.
Okay, thank you, Scott. Thank you, Carl. This is Sven from EM Engineering Methods. So we are a German-based company, and just to introduce EM in short, you can see our screen, I guess. So we were founded in 2001 in Darmstadt, which is located, let's say, 20 minutes south of Frankfurt. Maybe some of you know the Frankfurt Airport, which is a big hub in Europe. We are an engineering IT and consultancy company in the area of engineering, and with specific expertise and knowledge with CAD, CAE, PDM, and PLM. Our focus is more or less on processes and methods first, and then technology, which is tools and PLM IT environments within engineering. We have different partnerships. One of those is the partnership with Phoenix, where we provide Model Center for process integration, design optimization, but also for MBC. And saying that, we are also engaged within different chapters, like the German chapter of the INCOSI, but also the VDI, which is the German Association of Engineers, where we talk about mechatronic design, systems engineering in general, and how to apply methods, processes, and of course tools to industry and to our customers. We partner up with international customers, despite the fact that we are a German-based company and doing consultancy services and providing solutions throughout Europe. So there's a strong focus on automotive, the German automotive OEMs, suppliers, Tier 1, Tier 2s, but also some aerospace like Airbus and Rolls-Royce, consumer goods, and of course machinery and process industry. And maybe you heard about, we call it Industry 4.0, which is about how to bring the IT, how to bring in IP within machine industry. And there's a huge demand in German industry when it comes to systems engineering in order to enhance those capabilities. And of course, today I will talk about what's going on at Meyer, who is the world leader in textile machines. We are divided into 4 divisions, so we are talking about business processes, consultancy in general, doing process analysis, process enhancements, but also some specific topics like data exchange, requirements engineering, supply integration, or, of course, systems engineering and IT strategy. I'm the head of CAD and CAE, so we're talking about CAD, CATIA, NX, CAE, but also systems engineering and knowledge-based engineering. And I will have a focus on these issues today during my presentation. And in addition, we do have a software department where we build up our own products and tools, but also doing a lot of integration when it comes to multiple CAX solutions and how to integrate, how to streamline those applications within the engineering field. And last but not least, PDM, PLM, product data management, product lifecycle management, where it comes to data management, but also process integration, workflow management, and so on. The topic of systems engineering is widespread. So we do have, let's say, a systems engineering approach which covers all of our business units. So we do have interdisciplinary teams talking about introduction of SE, the V model, which is a technical process for mechatronic product design, but also strategy and organization, and of course methods and tools when it comes to the usage of MBC or systems engineering techniques and instruments in general. On the other hand side, systems engineering is still, let's say, a research topic. So we are cooperating with universities, but also with some of our innovative customers in order to enhance methods and tools for systems engineering in general. Why systems engineering? So what is the focus and the target which is addressed by systems engineering? One of the key arguments we most of the time are facing is we need to master the complexity of our system development, especially in early design stages. So the complexity of technical systems will grow or is still growing, so there's more electronics, there's more software in all of the products, and of course it's about management of interfaces and dependencies, not only from a system perspective, but also when it comes to organization. So we do have mechanical design departments, electrical design departments, and software. And of course, some do also have systems engineering capabilities, and it's about the management of the interaction of those design disciplines and departments. And of course, products have gone more complex. So this is a study, a result from a study which I did some years ago, where you can see the life cycle of some Beamers, some BMW V5 series over the last years. So the time for operation and the time for changing new series has been less from, let's say, 10 years to 4 plus 3 years, because today also facelifts are more or less new series, if you like. And of course, the number of parts, the parts relations, the interactions, the variants, and of course, software has been coming more and more complex. So there's a huge demand in order to master the complexity. Saying that, there's a possibility which SE offers when it comes to quality management and validation. So systems engineering offers techniques, instruments in order to confirm system properties, to safeguard quality by checking customer requirements, by looking at standards and doing some certifications, which are more or less also regulated by rules, by international rules, or by some rules which are specific for different industry sectors. And there's a high demand when it comes to traceability in order to manage the interfaces and dependencies, not only from product perspective, but also when it comes to data, to documents, to data, and to tools within the engineering departments. And of course, there's a high demand in order to reduce hardware and prototypes. So there's no chance to check every prototype by doing a test model or doing a pilot model. There must be more and more virtual development methods and tools in order to go from real hardware testing to virtual testing. And that means that we need to have front-loading and simulation in early design stages. And this is really a high demand within automobile industry, but also more and more in machinery and process industry. And of course, saying that mechatronic design or general engineering today is led by different disciplines. SE, systems engineering, enables the cooperative development process for multidisciplinary engineering. So this is kind of common language which is provided by systems engineering. So after all, systems engineering is an interdisciplinary approach in order to enable successful product or system development. We do have customer needs which need to be defined. Requirements management and engineering is the keyword here. And then proceeding with systems synthesizes and system validation, but also covering operation, cost and schedule, performance training, and other issues. And based on the Systems Engineering Handbook, which is, let's say, the Bible from the international chapter of the Systems Engineering Group, we find that there are different processes mentioned in this handbook. Of course, we will focus only on technical processes today, but also there are some project enabling processes, agreement process, and project processes which need to be taken into account, because most of the time these kind of customers using systems engineering, they will also talk to suppliers or to OEMs. They will have a strategy on their product. So all these different processes are basically described in the SE handbook. When it comes to the introduction of systems engineering, you need to be very focused on which portion you will focus on, which means what is your target, what is your goal in order to introduce systems engineering. So today I'm focusing more or less on the technical processes, on model-based systems engineering, which is a method, a process, and which also offers tools for the early design phases when it comes to the requirements definition and analysis, to architectural design in the concept design phase, and also implementation in order to design mechanics, electrics, electronics, and do control unit design in the machinery industry. The technical process is also described within the so-called V model, which is very common in Germany. So there's a regulation which is called VDI 2206, which is the design method for mechatronic design. And based on requirements from the market or from customers or from the stakeholders in general, the engineering process is starting with requirements engineering. And then we do have a long tradition in Germany to do a design in a kind of methodology way. So we're talking about functional design, logical design, and physical design. Of course, this is very simple approach in order to outline the system analysis, but we will have a closer look in some minutes. And of course, the most important issue here is what about the requirements? Are the requirements covered? Are the requirements described? And how can we take down the requirements within this system analysis process? Based on a system architecture, which is the outcome of a physical design, then we hand over to the departments which are doing component design or subsystem design. And here we do have the specific disciplines like mechanics, electronics, and software. And we're talking about system development. Of course, this is a very easy let's say, graphic in order to outline the V model. Of course, we do have more than one V model. Sometimes we do have one for electronics, one for software, one for mechanics. We do have also V models not only on our side, on customer side, which is the OEM, for instance, or also on supplier side. Of course, in this early design stage and within system development, a lot of engineering data evolves. And we need to address the management of this engineering data before it comes to system integration, where we do have component testing on a virtual base, but also on hardware. Some of our customers already using XIL, which is model in the loop, hardware in the loop, or software in the loop technologies. And then we do have the integration within the real product or real subsystem before we verify our functional design and validate the requirements against our system which has been developed and released. And of course, simulation and test and the results gained from that will be feedback to the system analysis in order to check whether the requirements are fulfilled or not. And of course, we do have a lot of iterations which are not shown in these pictures, but of course, it's a more or less iterative process in general. Product lifecycle management and, of course, engineering process data management is key, and that's an issue when it comes to the IT environment for systems engineering or model-based engineering in general. So what is model-based systems engineering? In the early design phase, we are talking about requirements, functional design, logical design, and of course, there is some possibility where you can use SysML, which is the systems modeling language, in order to describe those kind of aspects of artifacts within a systems engineering model. So this is based on the UML language, and some customers do have gained some great experience. Other customers, which are not familiar with those kind of techniques, they ask for that, but need to be supported, and that's what we did at Meyer, which will I present in a minute. And of course, you should be familiar with the expert engineering design departments and the tools, which is mechanical CAD, electrical CAD, software environments like IDEs or CAE or 1D behavior modelings in order to safeguard the multiphasic models. Model-based systems engineering is the application of tools, of models within the systems engineering process. And the question is how to integrate, how to communicate from an early design phase, which could be led by a system engineer or systems engineer, and cooperate with a component or subsystems engineer. And in this case, most of the time we detect a lot of different tools. So there is Rhapsody or Cameo, for instance. There is Enterprise Architect. Maybe there's Untitled or a PTC modeler in place dealing with SysML. And of course, we have a lot of CAD systems, ECAD systems, software development environments, simulation tools, and so on. And these are most or less used in specific departments. They have a specific need and do the specific work. And the question is how to integrate and how to streamline the process within engineering when using these tools. And here, Model Center as a federative approach and a solution could help in order to orchestrate those models and the activities I mentioned, like Scott was presenting earlier. So specific in some custom areas where we have a lot of different IT tools, Model Center could help not only to orchestrate different tools and streamline processes, but also to support the model-based systems engineering in order to link the requirements, the parameters from the early design phase to the component or subsystem design engineering, but also to feedback the results from simulation and to compare whether the requirements fulfilled or not. So for today, I would like to show you one example which was taken from our customer, Meyer. Meyer produces textile machines worldwide. Market number one is China, but still they are German-based companies. They have their headquarters near Frankfurt, Germany. They have different business units in order to produce different fabrics and textiles on their machines, from nice gowns to sport textiles, but also technical textiles like carbon fiber, but also fiber for seating in cars, like you can see here for the BMW i3. And besides different machines, they're also doing component design and manufacturing, and because they need to enhance the dynamics of their machine, they went from steel to carbon fiber, and of course they have their own component manufacturing from carbon fiber, which also delivers components to automotive industry or other industries too. So 3 years ago, the engineering manager and the IT manager asked us if we can support Meyer in order to go from the mechanical design, mechanical engineering focused development to a more or less mechatronic based design. And the question was how they can introduce the mechatronic way of engineering in general. So the vision and the goal was to introduce a mechatronic product development process and, of course, model-based systems engineering, because in earlier years the mechanic design department was always in the lead, which means that 200 or 300 mechanical engineers were starting the development of a machine, of a textile machine, like you can see here, and then electronic or electric design took over, and last but not least, the software developers, which are responsible for controller design, took over in order to get the machine running and to meet the specification, the requirements. So there was a need for a mechatronic product development process, and of course the introduction of MBSE, Model-Based Systems Engineering, which covers requirements engineering and management, of course computational engineering in an early design stage in order to get rid of prototypes and hardware test rigs. And of course, they wanted to test and learn MBSE first before they wanted to deploy, to roll out MBSE on a global scale. So we were talking about pilot projects first, saying we were doing some laboratories on specific use cases in order to test whether requirements engineering management using of SysML, multi-domain, 1D, CAE, and other tools would fit into the engineering departments. And of course, we're enhancing the processes by doing some process integration and design optimization. And when we started back in 2012, we had one lab, which was the string bar development. So this was the first laboratory in order to develop according to the V model and the VDI 2206 methodology in order to demonstrate the model-based approach to define requirements on a fully scale, which means we need to fulfill the determination of requirements, to address all the different requirements, not only from the mechanical design department, but also from electrics and software. And of course, to introduce Simulation X, which is a tool for multiphysics for 1D CAE. So Simulation X will allow engineers not only to discover mechanics, but also the overall systems behavior, mechanics, electronics, which means motor units, for instance, but also controller design, and to study the behavior of the overall machine in an early design stage, or not only machine, but also some subsystems like the string bar. So the outline of this first pilot project was to define the use cases and derive the requirements from those use cases according to the string bar system, to define the system architecture and to model the system behavior afterwards. The string bar system is a very specific part where all the needles for textile machines are put on, and it's very complex and it needs to be very precise in order to have really fine fabrics afterwards. And there was a technical problem saying that there was a speed limit when it comes to their recent architecture, and the question was, how can we produce more fabrics within 1 hour by setting up a new system architecture. So this was more or less a conceptual design in order to gain a new system architecture for the string bar solution. So we did a modeling of system behavior and simulation in order to evaluate different designs in the early design stage to get the best result of one concept. And of course, after we selected one concept, we modified parameters, we modified some constraints in order to optimize, to enhance this concept. So we started with requirements engineering using Cameo, which was a magic draw before. We did a functional design by using a functionality method, which is called the FAS, the Functional Architecture of Systems approach. There are some other methods available, like the RFLP, Requirements Functional Logical or Physical Design. There is Consens available. There is Sysmod available, but we decided to go with the FAS method here, and we derived from the functional design a system architecture, and we're modeling this system architecture and its behavior using the Simulation X tool for the 1D multiphysics simulation. And after all, we decided to design also the new concept for a string bar within CATIA to gain the geometry model within the CAD system. So the optimization was about have a look on the motion, which is like I said before, more or less a mechatronic approach, having different bars, different mechanical linkages and bar systems in order to define the movement of the needles, which you can see here, or in this picture here, where you see the fabrics or the string for the fabric design. So the first task was to design the mechatronic drive concept using SysML on a conceptual layer, and afterwards we defined system architecture, and this is a very simple representation of one of those concepts, saying that there's the needle, which is represented as a single needle here. We had to have a spring damper system for the bar itself, for the string bar, and we do have a motor which is controlled by a control unit, and of course a pneumatic cylinder which rejects the string bars in this direction. So this was the first concept. We have more than 3 or 4 concepts right now, which I couldn't present because it's disclosed. But to give you an idea of what we're dealing about, so it's about the mechanic plant, the mechanic process for the string bar. We do have the motor unit and, of course, some control unit, which needs to be defined based on the functional architecture and the system architecture. And after all, the question was for this use case 1, for this laboratory, which is the best concept and which is the optimal design. So it's not about the concept itself, it's also about which kind of parameters, which kind of dependencies we need to check, and how can we optimize the first concept design. So we were thinking about the engineering IT environment. There was no Cameo nor SysML editor in general available, so we decided to go with Cameo Systems Modeler, and of course Excel, which is mainly used when it comes to requirements, and we were coupling Cameo with Excel. The SysML, of course, within Cameo itself, and for the product development, for the mechanical parts, we were using CATIA V5. There was some HyperWorks motion view available for mechanics, dynamics, multi-body simulation, ePlan for ECAD, and of course for controller design, MATLAB Simulink, and for multi-domain CA simulation, ITI's Simulation X. These were standalone tools, as I mentioned earlier, so we need to have a tool environment for process integration and design optimization, which was Model Center and is still Model Center at Meyer. So like you can see here, we have different aspects to cover, from systems requirements to functional design, logical design, multi-domain simulation, and physical design. And Model Center is more or less our federated platform in order to orchestrate all these different aspects which were supported by tools which I was mentioning. So what is the use case in practice? At first, we have to have a look on SysML modeling. So based on the specifications we developed a requirements management for system modeling, and based on that, we were deriving functions, a functional structure, and decided to have some parameters which are key in order to derive system architecture. But also you can see this linkage here. It's more or less also a feedback approach. It's a lot of iteration, and we will show in a second how it will work in Cameo. So I would like to hand over to Robert, who is one of our CAE and CAD experts in the area of my business units, and he will show you Cameo Systems Model on this example.
Okay, hello from me too to everyone. I would like to show you a little bit of the model and the Cameo Systems Modeler. It's built, as Sven said earlier, in SysML, and I would like to especially focus on why we have advantages in using a SysML modeler for the requirements instead of using Excel or Word documents. So we would start out by putting our system in the middle here, and at first to look at what will influence our system and what will be influenced by our system, and create a context map of things around our system, so we can see where we should interact with, where we get requirements from. Once we get the requirements, we put them in this diagram form. I can go through here. The advantages are I can use the requirements, I can organize them, and then I can also put them into the dependence from each other. For instance, this one is derived from this one, and so I can organize them or prioritize them in any way I would like to. But I can also use the Cameo modeler to get a requirements list, as you might have in your Excel, in your Word, or in your IBM DOORS, for instance. And then I can derive a functional view on things and get the functions that my system needs to fulfill, and the information and data and energy that is transferred in between those functions. And now as another advantage, I can also do evaluations of this, as I can, for instance, what I will show here is the requirements are displayed here, and I can now check out if every requirement is fulfilled by a function. And I can do this in the later stages as well with the architecture and the components and so on. Okay, so much to requirements in Fmea. I will now give back to Sven.
Thanks, Robert. Having this system architecture set up, the next step is now to hand over to the experts, the domain experts from different disciplines. And here, this is a picture how Model Center supports this process from the early design based on SysML models to the domain models. And the question is how to check if the requirements are fulfilled or not. This is one question. So we hand over the parameters, we do some simulation, which we'll see in a minute, and then feed back the results using Model Center MBSEPAC in order to give the systems engineer the capability to check whether requirements are fulfilled or not. So the question is not only to check the requirements at any time, but also to integrate the data from different disciplines, from different tools, especially when it comes to simulation, using Simulation X here, and to ensure if we do have more variants, more parameters to analyze, how can we optimize this kind of process in order to streamline the engineering work. Of course, the feedback will result in an understanding and assessment of the impact of changes as well. So if you would change parameters or concept, what will be the impact? That's a question which will be answered by Model Center MBSEPAC as well. And of course, to optimize the computation and simulation process, as I mentioned earlier. To run the demo in short, we prepared some AVI here, where you can see the environment for Model Center, the framework, where you can see different tools which are integrated. So we have here some different concepts set up in order to investigate our design concept. So this is concept number 1, which I was outlining before, another concept number 2 and 3. And you can see here how Model Center MBSEPAC will feed back the results from simulation and will compare the results from simulation with the requirements. For instance, if the positioning will be achieved or not, or some other requirements will fulfilled or not, and you can see here the positioning will not fulfilled. So we need to change the concept, or we need to change some parameters within the engineering and simulation model, and we'll run another simulation task in order to check whether the requirements are fulfilled or not. So Model Center and MBSEPAC will help to understand the overall conceptual design in an early design stage, and will safeguard some parameters. And the Model Center framework, the overall model, consists of the simulation model, which is represented by 1D simulation within Simulation X on one hand side. On the other hand side, you can see here some icons, some symbols representing the Cameo requirements model and parameter model, which will be linked to our simulation in order to check if the requirements are fulfilled or not. We can close this AVI here, and I will show you later a URL where you can check this video, this AVI, and some more information if you like. So back to the presentation. The results from this first lab was that MBC, based on the VDI and the functional architecture of systems methodology, could support the systems analyze and design. So here are some outcomes. For instance, when it comes to positioning, the red line indicates whether the positioning of a needle will fulfill the requirement. So we need to pass this area here and this area here, and you can see obviously this is not fulfilled here. On the other hand side, there's another concept where you can see, okay, we do have some better results, but we need to adjust in some way. So after all, the result was that Model Center dashboards the results and can enable MBC at Meyer. That's why we come up right now with another use case. At first, we started also with a laboratory, but we can say since last year, end of last year, this is really used in productive design and helps the engineers at Meyer to streamline their processes. So I will hand over to Robert again.
Okay, so the use case is the following. At times, the thread that is rolled onto this drum that you see here in this picture can break. And then once it's broken, it needs to be well repaired, and then the drum needs to get rolling again. And the faster this goes, the better it is for the company that uses the machine. So it's a selling point. So what we did here is provide a 1D simulation of the whole system. It consists of 3 parts. We have the motor on the left side with the motor power and a very basic controller and the maximum torque. And then we have on the right side the thread itself, which pulls with the force because it needs to be in tension. And so what we need for a simulation is the inertia of the drum that we will be using. We might be using different drums in different machines. And we get that drum from a CAD model in CATIA, and now it needs to be supplied into the CIMIC simulation, and that's where Model Center comes into play. We have a model in CATIA which is parameterized, and we can enter these parameters here in the Model Center GUI. And then I will do this right now. This is live in the tool. I can enter a value here and then redesign the part in CATIA. So now CATIA will measure my inertia right here, and I need to give this inertia over to CIMIC, which I can do using the link editor. So I hover over here, and I slide this down, and then I go into my CATIA. I get the value that I want to give from CATIA to my simulation X, and then via drag and drop, I can make this line, which symbolizes just the connection between these 2 software tools, which Model Center helps me orchestrate. So I give this to the simulation X, and then I use the scripting component to get some more data from it. In this case, it will calculate when a certain desired speed is reached after what time. Just to show you that you can also, instead of just orchestrating tools into your workflow, you can also script stuff yourself, which is being done here. So let me just change a little something. I will take the power of the engine of the motor down a little bit and start the workflow. And as you can see, it's running now. It's running now the simulation in Simulation X. I'm sorry about this. It's not going to work because I need to close this. I'm sorry for this hiccup. I need to close it so that Model Center can run smoothly. All right, so let me do this again. So I changed the power of the motor, and now CATIA will redesign the drum, and now Simulation X will run the simulation with the new values that have been measured by CATIA, and then hand over the results to the calculation and give me my new time where my desired speed is reached. And yes, it's finished now, and as you can see, the time has changed. It's gotten longer, which makes sense because the power went down. Now what I have here is a workflow which I don't have to do any manual work anymore. I put my models in, and Model Center will just help me transfer the parameters. So it will really help me if I do this lots of times. So what I can do with Model Center as well, with the Explore part of it, is do a design of experiments. So just get valuables as design variables, define some ranges, define a search pattern, and then just run a lot of runs at once. And I'll just show you very quickly how easy it is. I can just drag and drop my response that I want to measure, my time where the desired speed is reached. I can just drag and drop it in here and then start it. Of course, I won't do it now, but I have earlier today. And I would like to show you the visualization. So this was 500 runs. And what we can see here is every little cube represents one run. And now we can get a very good understanding of the system at hand. For instance, which makes sense if I give my motor more power, of course the time to reach a certain speed goes down. And I can analyze this the other way around. If I enlarge the part, if I enlarge the drum, the time to reach a certain speed will go up. So much for the use of Model Center and MBSE, and then it's back to Sven again.
Yes. So the objective today is for drum design to go from requirements, different machine types for different textile machine environments, in order to set up the right powertrain unit, to set up the right parameters. Of course, at Meyer within the Department for Drum Design, they're now using SysML for requirements engineering. If there's a new concept necessary, they go to doing a functional architecture. They represent their design principles within SysML as well. Of course, the interconnection between UML, SysML, and CAD design is managed by Model Center. So, like you can see here, today they have a specific requirements model based on the, let's say, main requirements. They have a display in order to understand the functionality of their drum system, which is a common language now for not only mechanical engineers but also the electrics, electronics, and control designers. And of course, this Simulation X model was very helpful in order to evaluate designs in an early design stage, or to do some parameter studies or some optimization. So Model Center is now one of the key solutions within the design department when it comes to drum design. What are the experience we took from Meyer, or Meyer took by itself during the last 2 years? So they found out that Model Center is the tool which can integrate different tools within the engineering department, which can support parameter and design studies, and also doing design optimization, including with links to MATLAB Simulink or Simulation X. And of course, they can have a real good understanding by using the dashboard and the reporting functionalities of Model Center. So the outcome and the result is that they gained a better understanding and higher understanding, because of interdisciplinary communication will be supported by using different tools, but also Model Center for federation. They can trace now the requirements. The main requirements, which are the most important one, can hunt over through the design steps which we outlined today. And of course, first step for multi-domain simulation results in less hardware prototypes and testing. So of course, the parameters for all the simulation models need to be identified, but we can have upfront simulation before 1 or 2 prototype and test rigs could be or will be used. And of course, design optimization and design studies using sensitivity analysis or design of experience helps to support decision making and taking. And last but not least, because of Model Center's integration capabilities, different tools could be linked and coupled in order to streamline their engineering process. So last but not least, I would like to summarize the Model Center approach and the MBC approach could optimize the mechatronic development process. The systems engineering approach based on the functional architecture of systems methods could faster adapt some requirements and can control changes. And of course, we need to have an environment which can support different best-in-class tools by doing integration within an existing IT landscape. Last but not least, it's always important to talk about the strategy when it comes to the introduction. At Meyer, we decided and consult in order to have some laboratories first, because they were very weak when it comes to systems engineering 3 years ago. Then we decided to convince the key stakeholders, the engineers, but also the management, by having some use cases, some laboratories. And now, after, let's say, 3 or 4 laboratories, we found out where are the use cases which can be supported. But of course, we failed also in some laboratories. So to be honest, not every use case would be supported successful in terms of tools, but also in terms of organizational architecture and understanding. So there's still a challenge to convince everybody to introduce MBSE. But like we showed today, there are some really good reference stories where we can convince not only customers but also general stakeholders. So thanks for your attention, and we are ready to take your questions.
All right, thank you very much, Sven. As a reminder, please use the Q&A feature in your WebEx window to ask your questions, not the chat feature. Also, please be sure to send your questions to all panelists. You will not be able to see your question once it's been submitted, but please be assured we will try to address as many questions as possible today. If we are unable to get to your question, or if you have additional questions following the presentation, please don't hesitate to contact us. I'll now turn things back over to Scott Reagan, who will handle the Q&A section of the call.
Okay, thank you very much, Sven, and thank you, Carl. I have one question that just came in for you, Sven. How long did it take your team to integrate the drum analysis in Model Center?
I think this could be answered by Robert because he was one of our key consultants at Meyer.
Yeah, since it was one of the first projects we did, it was a matter of familiarizing ourselves with the software first. So it's very hard to say, but with our knowledge that we have now in the company, if we have the models parameterized right, and if the specific models are done, it's a day's work.
Okay, thank you. Another one for you, Sven. What was the most challenging aspect of the project working with Carl Meyer?
So we were dealing with engineers from the mechanical design departments first. So most challenging was to introduce system modeling techniques. Because mechanic engineers are not familiar with SysML or UML style notations because it's very abstract. But based on the VDI guideline and their knowledge of methods, we started with flip charts, with brown papers, with whiteboard style, and then went over from, let's say, a more or less conceptual paperwork-based modeling to SysML. And of course, there was a discussion who would be in charge of systems engineering or system modeling later. So we changed the organization in order to introduce a systems engineer. But this was more or less the first challenge and the biggest challenge to bring in systems thinking to the customer environment and to convince that SysML would help to understand their product, their systems better, and to come up with better solution in future.
Okay, thank you. Next question. How much time did it take for Model Center to generate the surface plot that you displayed? And as a follow-on question, what was driving that time? Was it dependent on Model Center or other aspects?
It's mostly other aspects. The simulation, X simulation is the longest, as I would say. But as you've seen one run go through, and that's with all the software and the WebEx and everything open on my laptop. So to answer your question precisely, it was 44 minutes for 500 runs. But it strongly depends, of course, on the simulations that Model Center itself orchestrates. Model Center itself doesn't take a lot of time. It's the simulation that it addresses that take the time. So for this specific example, 500 runs, and it was 44 minutes.
Okay, thank you. Next question, and this is for EM. In introducing a systems engineering approach and tool set to Carl Meyer, was there significant resistance from engineering, and was there same for management? And did you have a training model strategy for getting individuals on board?
Yes, good question. Thank you. Based on this so-called federated approach, we didn't change the IT environment in general. So we stick to those tools which are best in class, which were used at Meyer for a couple of years. And what we introduced was Cameo for the early design of systems models, requirements, functional design. And of course, like I mentioned earlier, this is now an issue for their systems engineers. So they have two systems engineers right now, and their task is to have more on board in future. And of course, we do have an education program in order to introduce systems thinking in general, to do SysML modeling more precisely, and also to use Cameo or like other editors too, like Rhapsody or others, to get started. But there's more or less not only a training available or necessary for IT tools. It's more or less how to define system models, how to model function aspects, how to come from, how to get from requirements to functions, from functions to system architecture. And of course, we do a lot of consultancy within, let's say, 2 or 3 projects up front before the systems engineer can do the work by themselves. When it comes to Model Center, there was a really high demand after they understand what is the capability and how easy it is to link different tools and to set up a process chain and to integrate processes. And in addition, they are using the Model Center Explorer in order to optimize their design or do some parameter studies. So this was not a big issue, but the SysML modeling and the introduction was a big issue, and it's about system thinking and how to do SysML modeling first. That takes education, of course.
Thank you, Sven. The next question, is it possible to get a copy of the charts as talking points to our team and encourage participation in the next meeting? And I think the answer to that's yes. Is that right, Sven?
Yes. Yeah. So
we will be posting a recording of this webinar on the Phoenix Integration website, and also will there be a download available directly from our website? Okay. Yeah. Okay. Moving on to the next question. Is there a direct connection from Model Center to your PLM CAD environment to do the redesign of the drum part? And does the SysML model play any part in this connection?
Yes, there's a direct interface. At Meyer, they are using CATIA V5, but Model Center offers also other direct interfaces using API technology of NX from Siemens PLM or Inventor or SolidWorks. So there's a lot of capability for direct integration, yes.
Okay, thank you. Can you describe any methods you may have used to ensure that future changes to your model could be easily incorporated? In other words, how did you design your system model to be adaptable and reusable in the future?
So we designed the system model by using Cameo, and we outlined or tagged or marked the parameters and the requirements which will be changed in future. So we were thinking about in the design phase which kind of adaptations, which kind of changes could be occur, and thinking in changes and iterations, we come up with a modeling technique within Cameo where we tag these parameters, and of course we have a documentation available for this model, and we have specific training for drum design, for instance, in order to deploy those kind of methods and tools to different engineers.
Okay, thank you. So I'm not seeing any more questions at this point. We do have time to answer a couple more if someone has additional questions. We'll wait a few minutes. I do want to point out that our next webinar will be on Thursday, March 24th at 2 p.m. Eastern Standard Time, and that will be presented by Mr. Bryce Martin at Lockheed Martin Space Systems, and he will be talking about a similar topic, actually, how they used Model Center MBSE Pack to connect IBM Rational Rhapsody to system conceptual analysis tools. Any more questions for Sven? We're getting, just got one more here. Is an Fmea analysis typically used? So failure modes and effects analysis. How is it integrated? Sven, did you hear the question?
I'm sorry, I didn't get it. Could you please repeat?
Sure. Is a failure modes and effects analysis typically used? And if so, how is it integrated?
Yes, of course. Okay, so we're talking about Fmea. So most cases, Fmea is a standard method within industry, and of course, Fmea will be derived from functional structure. So we found out, or not we, but we knew, Carl Meyer found out that if they are doing the SysML modeling and doing a functional design, they can derive Fmea automatically. And of course, by checking the system context, the overall system context using the SysML technology, they found out that also other boundary conditions or influences could be covered within the Fmea, which they didn't know before. So of course, yes, SysML can be used and could be enhanced the Fmea.
Okay, thank you, Sven. I'm not seeing any more questions, so I'll turn things back over to you, Carl, to wrap up.
Excellent. Well, thank you very much, Sven, and thank you, Robert. We greatly appreciate the excellent presentation today, and thank you to Scott and all of today's attendees. As Scott noted, our next webinar will be on Thursday, March 24th, 2016 at 2 p.m. Eastern Standard Time, entitled System Trade Studies and Design Optimization, presented by Mr. Bryce Martin from Lockheed Martin Space Systems. We'll leave the poll active for just a few more minutes. If you hadn't had a chance to complete the poll yet, please do so. And thank you again for your interest in Phoenix Integration. Have a great day.
Thank you very much. Bye-bye.